Assalamu alaikum warahmatullah. Welcome to my class on distributed and parallel computing. You will find all videos on my YouTube channel, so don't forget to subscribe and click the bell to receive all updates. Okay, our topic today is all about the parallel computer memory architectures. In our previous classes, actually, we have covered some information about the parallel computer memory architecture. And as you remember, we have discussed some things related to the shared memory. We have discussed some things that related to distributed memory and so on. So for today, we are going to cover all of that stuff with more details. Then after that, we have to go to something called parallel programming models. Okay, so this coverage here about the memory architecture is only to introduce you to the programming models. Okay, so the things or the models or architectures that we have to take today is three. Number one is shared memory. Number two is distributed memory. Number three is hybrid distributed shared memory. So in the third architecture, we have a combination of the first and second architectures together in the same system, as it's clear from the name. Okay, let us come quickly to the shared memory architecture. Shared memory architecture, as I said in the previous class, all CPUs have only one shared memory. So that shared memory will work like a whiteboard. So somebody can write at a time and other people can read, right? So to reflect that on the computer, that means one CPU can write at a time and others can read. Okay, so here shared memory parallel computers vary widely, which is means this kind of architecture is well known and available everywhere, but generally have in common the ability for the processors to access all memory as a global address space. So the ability of CPU here is to read the entire global memory, and all data related to CPU number one can be read by other CPUs at any time, and vice versa. So there is no private, no private memory for certain CPU. All memories are sharing the same global memory. Multiple processors can operate independently but share the same memory resources. So here every CPU can run independently without being synchronized with other CPUs, but they have to share the same memory. So in case two or three CPUs want to read or want to deal with the same variable in the memory, for example, then, for example, CPU number one wants to update that variable, the others have to wait. The other CPUs have to wait. This is what they call it synchronization. So in order to do that synchronization, there are many techniques. There are lock semaphores. Many techniques can be used. Okay. The third point here, changes in a memory location affected by one processor are visible to all other processors. So any change in the memory by a certain CPU will affect all other CPUs. So that data will affect all other CPUs because that data definitely is written or saved on a global shared memory. The last point here, shared memory machines can be divided into two main classes based on memory access time. The first class is called UMA, the second class is called NUMA. Okay, what is that? Okay, here in this slide, we will know what is the difference between UMA and NUMA. So UMA means Uniform Memory Access. In the Uniform Memory Access, both of them, by the way, are shared memory, okay? We still under the shared memory. So UMA, most commonly represented today by symmetric multiprocessor, which is called SMP machines. SMP machines. So this kind of machines or this kind of architecture, they have identical processors. Identical processors. So if let's say, for example, if let's say they have four processors, all of that four processors have to be from the same family, from the same and using the same frequency, same speed, same everything is same clock rate, everything is the same. Okay. So this is what does it mean by identical processors. Here, each processor has equal access and access times to memory. So all of the processors can access the memory fairly. So they have the same amount of time to access. They have also the same speed to access, and so on. Okay, sometimes called CCUMA. CCUMA means cache coherent UMA. Cache coherent means if one processor updates a location in a shared memory, all the other processors know about the update, which is the main concept actually of the shared memory. But the technique here is using the cache coherent. Okay, so cache coherent is accomplished at the hardware level. So this one will require some components of hardware. Okay, the second class actually is called guys. One important thing when I say the first class and the second class, it doesn't mean ranking. It means first group and second group only, or first type and second type. There is no ranking actually. That mean it doesn't mean that the first one is better than the second one. Okay, is that clear, guys?
Clear, doctor?
Yeah.
Yeah.
So here we have non-uniform memory access. So this one actually often made by physically linking two or more SMBs. So this one SMB is uniform memory access, right? So this SMB have to fulfill all the conditions of the UMA. So the NUMA is a combination of two or more UMAs, okay? One SMB can directly access memory of another SMB. So they still can access the memories of other SMBs. Okay, let us draw something here to make it clear. Okay, I want to keep it side by side here to let you remember. So for the first one, UMA, what do we have? We have one shared memory. This one is memory. Okay, let me write M here. Okay, and we have also for example, processors, right? So in this case here, let us copy this to CMV to make copies of that. And again, we need to take another copy, we put it here. So all of these can access the memory, right? Can access the memory because the memory here is shared, right? So this is what they call it UMA architecture, right? And this is called also SMB, which means multi-processors, the symmetric multi-processors. Here, every processor is identical to the other processor, right? So let us take this, make it inside a box here, and let us call it SMB. Okay, this one is SMB. Okay, now SMB, as I said, all processors can read the entire shared memory because the memory here is global and shared, right? So any change done by processor number one will affect all other processors. What's about the NUMA? NUMA can be a combination of multiple SMBs, okay? Those SMBs actually still can access each other's memory, okay? Because each SMB have its own memory, right? And the other systems, all SMB has memory, right? But still, the SMB, for example, number 3 can access the SMB memory of, the memory of SMB 1, and vice versa. So to do so, they have to have a network to communicate, right? They still have to have a network to communicate. So that network actually is used to exchange the data and information from SMB's memories. Okay, so here directly, if we change anything in the memory of this SMB here, it will directly affect these processors, the local processors. But other processors will not be directly affected unless they want to read or access that memory information through the network. So in that case, they also will get their result affected by the change or by the update in the SMB number 4 memory. Okay? Here, one important thing. Inside each SMB, the processors have to be identical. But among all SMBs, the processors not necessary to be the same. So maybe these processors, maybe processors here of SMB number 1 here, all processors are, for example, 2.4. For example, only guys, for example, here, all processors are 2.4 megahertz, gigahertz. And here for this SMB, the processors are only 2.1, for example. And here in this SMB, maybe processors are only 1.7. And here maybe something else, maybe 2.4 or whatever. Okay? So locally inside each SMB, all processors have to be identical, have to have the same specification. Exactly, the same technology, the same specification. But the other SMBs or the other UMAs are not necessarily to be the same. Okay? Then all of them have to be connected through the memory network, or what they call it, memory bus sometimes, or yeah, depends on the name. In many books you find different terminologies. Now we want to call it only network. Okay, only network that communicates or that connects the parts of the system. Okay, is that clear, guys?
Yes, doctor.
So here, point number 2, one SMB can directly access memory of another SMB. So from here, we can access the memory of the other SMB and vice versa. Not all processors have equal access time to all memories. Why? Because here, processors inside this SMB have equal access time, right, to their memory. But when another processor comes from another SMB wants to access this memory, it will not have the same amount of time. to access. Okay, that's why not all processors have equal access time to all memories. Then memory access across link is slower, because here when we want to access the memory from SMB number 4 to SMB number 1, we have to go through the network, and this network could be could have congestion, data congestion, or traffic congestion. So in this case, it would be slower than the direct connection to the local memory. Okay, this is one of the disadvantages actually. Memory access across link is slower, as I mentioned. Then if cache coherency is maintained, similar to this here, to the UMA, then it may be also called CCNUMA, which means cache coherence NOMA, cache coherence NUMA. Okay, so that's all about the UMA and NUMA. Here, we to remind you guys, we still under the shared memory. Okay, so here shared memory pros and cons. Okay, pros means advantages, cons means disadvantages. So here advantages are global address space provides a user-friendly programming perspective to memory. Okay, so this one provide the global address space, or what does it called global memory, provides a user-friendly programming perspective to memory. Okay, so here programming is much easier compared to other architecture. Data sharing between tasks is both fast and uniform due to the proximity of memory to CPUs. Here, as I explained, the data sharing between tasks, which is run on different CPUs, or maybe on different threads on the same CPU, they are fast and uniform. Why? Because the processor is very near to the CPU. The processor is very near to the memory. Okay, so the time accessing data from memory and retrieving that data or updating it is not that slow. Okay, disadvantages here. Primary advantages is disadvantages. Primary disadvantage is the lack of scalability between memory and CPUs. Okay, scalability means extendability. So if let's say we want to make a computer scalable or architecture scalable, that means anytime we want to increase the number of processors or the size of memory, we easily can do that without any severe impact on the architecture. So adding more CPUs can geometrically increase traffic on the shared memory. Can geometrically increase traffic on the shared memory CPU path, and for cache coherent systems, geometrically increase traffic associated with cache memory management. Okay, to explain this, yeah, if let's say this is the architecture that we are talking about, what if, let us do Control Z to remove all of the yellow notations here. What if, for example, we want to expand, instead of this number of processors, we want to expand it to be 8, like that. So in this case, if let's say the system is scalable, right? Because we still can extend or expand the number of processors and the size of the memory. Because when we add a new SMB, the number of processors will increase, and also the memory, the global or the entire system memory will increase, right? Because here we have a new sizes or new parts of memory added to the system. Okay. At the same time, this actually comes on the expense of the speed, because sometimes this system accesses the memory of others. Here, this CPU access system from data from other SMB, and so on like that. So if let's say we have multiple accesses from multiple SMBs to another SMBs like that. So what will happen here? The network that connects the SMBs together, or connects the processing units and memory units, will become very crowded, and we will have a lot of traffic congestion. Then here the communication will become very slow. So when the communication becomes very slow, the entire performance of the system also will degrade. So we will have a lot of or a severe degradation of the system performance if, for example, we increases the number of processing units and memory components into the same system using the shared memory architecture. Okay, so this is the one of the very famous disadvantages for this architecture, for the shared memory architecture. Also, if we have cache coherency system, then we have the cache component, which is also a physical component. So that physical component have to be connected to the CPU and the memory, because it will play the role of intermediate layer between the CPU and memory. So in this case, that cache also cache management will become very hard whenever we increase the processing units. Programmer responsibility for synchronization constructs that ensure correct access of global memory. So here, the responsibility to ensure the correctness of memory access is all assigned to the programmer. The programmer is the number one or first class responsible person to do that synchronization. So if the programmer miss this kind of synchronization or make it wrongly, then the entire system will be affected. Okay, expense here. The last point. It becomes increasingly difficult and expensive to design and produce shared memory machines with ever increasing numbers of processors. So the cost actually is a very big issue when we talk about a huge processing machine or huge processing power machine. That has, for example, 64 processors, or maybe 1 to 8 processors, or a big number of processing units. So here it will become very expensive. The implementation of that kind of machine become very hard. Okay, let us move to what they call it, distributed memory architecture. Distributed memory architecture, as I said, previously in the previous class, every CPU has its own memory. Then all CPUs are connected to a network. So that CPU or processing unit could be a component, could be a CPU or processor, and could be a machine, could be a complete machine or independent machine. For example, clusters. So in clusters, we have big number of computers connected to a very high-speed network and managed by one unit called controlling unit to appear to the user as a one machine. Is that clear, guys? The definition, is it clear?
Yes.
Yeah, for distributed, as I said, we can use PCs, normal PCs, for example, for clustering. We can use normal PCs, for example, 5 or 6 PCs. Then we have one unit which is called controlling unit, then here we can use very high speed network and link all of that machine. Sorry, yeah. And link all of that computers to that network, then using certain software to control all of that computers and to encapsulate them in one virtual big machine. When I say virtual, it doesn't mean virtuality that we know. Here, virtual, that means it will look like one machine while it's not one machine. So here, any user from outside, maybe uploading a file to the FTP server, which is installed over a cluster. So here, this user uploads the file, but it see the server as only one single machine. So it uses, for example, FTP link or maybe a direct IP address with a port. So when we send that file, the file could be saved here, could be saved here, could be saved here, whatever, we don't care. Because this is not our responsibility, it's the responsibility of the cluster management or control management unit. Okay? So this kind of systems, actually, the cluster is one type of distributed memory architecture. Okay, so here like shared memory systems, distributed memory systems vary widely but share a common characteristic. Distributed memory systems require a communication network to connect interprocessor memory. So as I said, this unit actually could be a processor, and this is another processor, and all of that processors could be installed in the same big machine, supercomputer. Okay, or maybe this could be a computer and this is another computer, and all of these computers are linked or connected together using a very fast network. Okay, so processors have their own local memory addresses in one processor don't map to another processor. So there is no concept of global address space across all processors. So here we don't have a global memory space, okay? Because every processor have its own memory, and they have a local memory space, which is not affected by the other local memory spaces of other CPUs, okay? Because each processor has its own local memory, it operates independently. So fully independent. This kind of system is fully independent. Changes it makes to its local memory have no effect on the memory of other processors. So if this CPU changes something on this memory here, it's not going to affect other CPUs. Okay? Hence, the concept of cache coherency does not apply. Here, we don't have the concept of cache coherency. Okay? Oh, sorry. When a processor needs access to data in another processor, it's usually the task of the programmer. So here the programmer is responsible to exchange the data between or among CPU's memories. Okay? Here it's the task of the programmer to explicitly define how and when data is communicated. So synchronization between tasks is likewise the programmer's responsibility. So synchronization here is the responsibility of the programmer. Number one responsibility of the programmer. Okay? Yes.
Can you help explain what is cache coherency? Because I think I missed the definition of cache coherency.
I don't want to go there actually, because if I go there, there's a lot of details. So
No, just
cache,
definitionally.
yeah, if you want to understand what does it mean, what is the cache? Actually, the cache is a physical component. If you remember, if you attended the last class, we did a quick survey of the processors, right? We
Yeah,
have been through the
I know what
families.
cache is, but I don't
Uh,
know what is cache coherency. Yeah, that one I don't know.
Coherency means the strong link between the caches. Yeah. Do
Oh,
you know the definition of coherency? Coherence in, I don't know how coherence in Bahasa Melayu. I don't know what's the meaning, but if you translate it, maybe, yeah, coherent is the same meaning. So coherent, you see here, coherence is the quality of being logical and consistent. That means when we say that something called any system called coherent, that means everything is very solid. Everything is logical and very consistent and very solid. Okay, I don't know how to
okay, okay.
really explain the meaning of coherency, but that's is it actually. I don't have any other thing to explain.
Okay, okay.
Yeah. Uh, Actually, in computer, we have very common things called. One thing is called coherency, and the other concept is called coupling, like this. Is it? Oh, I don't know what's the meaning. Oh, sorry, this one is coupling, like this. This too actually is very common everywhere. If you go to software engineering, you'll find it. If you go to operating systems, you find it. If you go to networks, you find it. Everywhere you will find these two concepts. The difference between this, actually, the first one shows the consistency and the solidity of inside the system, from inside. Okay, and this one is among systems, or between systems, from system to each other, which is all about the outer links to other systems or to other components. So the cache is something internal. So to make the system more solid, more logical, more consistent, the cache coherency is very important. So when you have a cache memory in your CPU with a size bigger than other CPU, you see the difference of the performance. The performance will become very good, better, faster, and so on. Okay?
Okay, okay.
Yeah. I don't know whether I explained it this well or not. Uh, Cache coherency. I don't want to waste time because this one actually is out of the scope of the course, but I want to give you a quick view for that. Uh, Cache coherency, let's say UMA. Okay, let us take an image here. You see the cache actually is inside the CPU itself. As I explained in the last class when we did the quick survey for the CPUs from Intel, from other brands, right? So we see some CPUs have very small cache, some CPUs has L2 cache, some of them has L3 cache. Actually, L2 and L3 are different. Also, the architecture is different because L2 cache is a physical component, L3 cache is also another physical component, and their place actually is different. And also, the purpose of using them is different as well. So the concept of the cache actually is to make the CPU, or to create a very fast, very fast memory component that could handle, or that could carry some information temporarily for the CPU in order to guarantee fast performance. So instead, for the CPU, instead of bringing all the information from the memory, and the memory to access the memory actually from the CPU, you have to go through the I/O bus of the what they call it, motherboard. So that could be congested, then it could be slow. So that's why they take the information that's commonly used by the CPU and save it here inside the cache. So any information or data, save it in the memory, but frequently used by the CPU, they put it in the cache, which is very near to the CPU, to make it very fast. So here, if the concept of cache is available or implemented, that means we may have multiple copies in the caches here for the same component, for the same data, right? So maybe here we have a variable called x, for example, and that variable have some information saved in it. Then that CPU frequently uses the x, so that's why a copy have been saved in this cache, and also that CPU frequently uses the x. That's why the x is temporarily saved here in the cache. So here we will have multiple copies of the same piece of data. So here, this requires what they call it cache management. So cache management needs another component to handle the copies in order to make sure that all CPUs have the same data inside the same variable that has multiple copies. So if, let's say, X has been changed in this cache here, that cache management unit have to take that information, update it here in this memory, then update it in all copies at the other CPUs. Actually, the story is quite long. I tried to summarize it to make it very simple for you. So hopefully you understand what is the meaning of cache. Is that clear?
Yes. Thank you, Doctor. Can continue.
Cache actually is a very common concept, which is also applied for networks. So in networks also, for example, when we want to make the access to some websites very fast, we can use cache also. But to do that cache, or to implement that cache, we have to have something called proxy server. So we put the proxy server, or enable the proxy server at the gateway or at the router. Then that server should take or copy the frequently accessed websites, or the components of the websites that are frequently accessed by our users inside our network. They take a temporarily copy of that website components and save it locally on the gateway or the proxy server. So when another user requests that website, that data will come from the local copy. It's not going to come from the remote server. So the cache concept is available in many things, actually, inside the computer, outside the computer, in the network, in the database, in all aspects of computer, actually. Okay. Guys, dealing with the distributed and parallel computing, or distributed and parallel architectures, actually have to you have to open your mind for a lot of things, a lot of aspects, a lot of issues. So that's why every piece of things we talk about here, you have to understand. So if you cannot understand, please ask me. Thank you for this student who asked me about the cache coherency. Yeah, because I'm sure he wants to understand. He feels like there's something missed. He cannot understand, but that's why he asked. But if you attend the class and you see me or listen to me while I'm explaining some things that you never know and you don't understand from my explanations, and you don't ask, you never learn. So guys, please, if you have any question, just let me know. Don't skip anything, okay? Okay,
Okay, Doctor.
yes, thank you. When a processor needs access to data in another processor, it's usually the task of the programmer, as I said, to explicitly define how and when data is communicated. So the synchronization between tasks is likewise the programmer's responsibility. The network fabric used for data transfer varies widely. So to it can be as simple as Ethernet. So in some cluster systems and in some distributed memory systems, they use normal Ethernet network to link the processing components or the processing units. Okay. Some they use twisted pair, some use fiber, some use different type of networks. Yeah, it depends on what technology do you have and what is your budget and what is the application targeted. Yeah, all of that aspects have to be taken into account. Okay, now we already explained about the distributed memory, and here we have the pros and cons of that distributed memory architecture. So the advantages here, number one, memory is scalable with number of processors. So here, if we increase number of processors, the memory will increase directly, as you can see here. Every CPU, every processor has a memory with it, right? So if let's say one CPU has 10 gig, for example, or 8 gig memory, then if let's say we increase one CPU, one more CPU, then 8 gig memory will be increased, right? And so on. So memory is scalable with number of processors. Both of them can be increased. The number of the size of memory and the number of processors can be scalable, can be increased at any time. And increasing of the number of processors and the size of memory are proportionate. Okay. Proportionate means they have a relation between them. When we increase the number of processors, memory will increase. If we reduce the number of processors, memory will decrease. So each processor can rapidly access its own memory without interference and without the overhead incurred with trying to maintain cache coherency. Because here we don't have cache coherency, that's why we don't have any problem. We don't have the overhead to maintain the cache, and also we cannot have, we don't have also the interference. Interference could happen when multi-processors tries to access the same piece of data in the memory at the same time. So here we will have the interference, and at this moment we will have something called, we must have something called synchronization to avoid that problem from happening. Point number 4, cost effectiveness can use commodity off-the-shelf processors and networking. So here, especially in the clusters, we can easily go and buy another machine and plug it to the network with different CPU, with different size of memory, with different technology. Maybe that CPU has, for example, i7 processors, and the existing machines have, for example, i3 or maybe Pentium or whatever. There is no problem. Why? Because all of that hardware will be encapsulated by the what they call it, the distributed memory architecture software. Okay, so the cluster management system actually will encapsulate, will hide all of that details. Okay. Disadvantages. The programmer is responsible for many of the details associated with data communication between processors. So here the task of the programmer is getting more complicated. Okay. Number two, it may be difficult to map existing data structures based on global memory to this memory organization. So this is very hard. Actually, this is a very hard task to map the existing data structure based on global memory to the memory organization. It's a very hard and a very difficult task. Okay. Number three, non-uniform memory access, NOMA, times. Non-uniform memory access, NOMA times. Yeah, the times, the non-uniform memory access times are actually a big issue because here we don't have what they call it, identical access time among the processing units. Okay, so for example, the processing unit to access the local memory, it has more time and faster speed compared to accessing that local memory from outside or from other processing units. That's why it's called non-uniform memory access. Okay. Okay, let us here come to the hybrid distributed shared memory. So hybrid distributed shared memory means a combination between shared memory and distributed memory. That's why they call it distributed shared. Okay, so here summarizing a few of the key characteristics of shared and distributed memory machines. So architecture here, it could be CCUMA, CCNUMA, or distributed. So examples here from the real life. So for the CCUMA, we have all of that examples. So if, for example, you want to see what is that, you can go take this, copy, go to Google. This is only an example, okay? Oops, what is that? Okay, maybe that doesn't work because some names are already obsolete. That's why you cannot see them. So, for example, let us take the IBM Power 3. So here, I think it should show something here. Okay, the Power 3 was the successor of the B2SC derivative of the Power 2 and completed IBM's long-delayed transition from Power to Power PC. So this, if you want to learn about it, you can go read in the Wikipedia maybe, or in other resources. You will see what is the meaning of that Power 3, IBM Power 3, or maybe the Sun VX, or other things, other examples. Okay, so all of these actually are examples available in the real life. Some of them have been already obsolete, and some of them are still available. So if you can see here from the same vendor, for example, IBM, for the CCUMA, we have IBM Power 3, and for the CCNUMA, we have the IBM Power 4, which is called MCM. Okay, and also from the same brand, from the same vendor, we have also as distributed architecture, we have IBM SB2 and also IBM Blue Gene. Okay, so no matter what vendor, no matter what brand, there are a lot of examples of every architecture, and mostly every vendor have some examples of all available architectures. Okay. So here we have for the distributed, we have Create E3E, we have Masper, we have IBM SP2, we have IBM Blue Gene, and also for the CC Noma here we have IBM Power 4 and HB Exemplar, and also Sequent, SGI Origin. A lot of examples that have been available for a while, actually. Okay, the communication used for those examples or under this architecture are like this. So for the CCUMA, you can find some examples using MBI, some examples using threads, some examples uses OpenMB, and some uses what they call it share memory or shared memory. This one, shamim, means shared memory. Okay, so here definitions of all of that stuff. So MBI is called message passing interface. Actually, it's a library. This one is a library used for distributed computing. So that one actually uses the message passing technique between the processing units. The OpenMB actually is an implementation of multi-threading system. Okay, implementation of multi-threadings. The shared memory actually is a library of parallel programming library. Okay, let me delete this parallel programming library. And here we have something called ISV later. That ISV is called, or it's short form of independent software vendor, which means vendors like IBM, like Microsoft, like, yeah, independent software vendors. Okay, so here these technologies can be used for this architecture to communicate all of the processing units together. And also here, this communication technologies can be used for the NUMA, which is exactly the same, identical here between these two. So MBI can be used for UMA and NUMA, and also threads, OpenMB, shared memory. Here for distributed, we can see for distributed we can use only MBI. So the MBI is the only technique or the only library that could handle all types of architectures. Or I mean all types of distri architectures, UMA, NUMA, and distributed. That's why MBI is very common. MBI is very common. MBI actually is an open source library, guys. It's an open source library. If you want to go and see it, so MBI, you can go search it. MBI generally here, part of general group, not this, no. MBI library here. There is something called OpenMBI, which is open source high performance computing. So if you want to go and see it, so you can open the website, you can go and search about the download, how to download it, Control F, for example, download. Yeah, this is the link to download it here. Yes, and here you can see all of the available versions of that OpenMBI. Here you can see that all of them are source files. So this will download for you the source code. So this is current stable release downloads. So if you download this, this one is RPM, means for Red Hat Linux or SUSE Linux. So you can use it. This one is tar.bz, which is a compressed file like zib and rar. Okay. So this is version 4.1.0 SRC. And here you can see release 2 source, also release 4.1.1 release 2, this one release 1, but this one are pre-released, which is not considered stable yet. Okay, so if you want to deal with that, you can go and download. This one actually is the notes here. If you want to read about the notes, what's the differences between 4.1.0 and the previous versions. So you can find the difference here and what's new in this package. if you click here, you can download the source code and then you can compile it. You can use it for distributed computing. That's all about the MPI. Actually, this course, as I explained, actually is not very detailed because this course is 3+0. It's more theoretically than practically. But anyway, I will try my best to give you some sessions of hands-on how to build a parallel program, how to deal with threads maybe, or how to manage threads or something like that. Okay? Let us continue and finish the theoretical parts first. Then after that, we may take some sessions of practical. Okay, scalability here. Scalability of the UMA is here tens of processors. There are tens of types of processors that could be used for this architecture. Here we have hundreds of types of processors can be used. This one for distributed, we have thousands of types of processors can be used. So the distributed is more scalable than the shared memory architectures. So here, drawbacks or cons. Memory CPU bandwidth. Here is the link between the memory and the CPU. Bandwidth is very limited, and if the speed is very low, then the total performance of the system will become very slow as well. Here they have the same thing, memory CPU bandwidth, and also they have another problem which is called non-uniform access times. Because here in the NUMA, processors does not have uniform access time. They don't have identical access time to the memory. Okay. Then here distributed the system administration programming is hard to develop and maintain. So the administration of the system is hard because here we have multiple distributed systems or processing units connected to each other using a fast network. So the management or the administration of the entire system is quite hard. So it needs a team of technicians. So maybe some could administrate the network, some could administrate the systems itself, and so on. Then the programming is hard to develop and maintain. Why? Because the programmer have a lot of responsibilities to do. Yeah. Then the software availability here, software availability in the market. Here we have thousands of softwares from different vendors. And here we have also thousands of softwares from different vendors. Here we have hundreds of softwares from different vendors. So here in terms of software availability, for the shared memory, we have more softwares available in the market. Why? Because those softwares will not have to take care about all of the underlying processing and communication. But here, in this case, for distributed, softwares have to take care about the distribution and the system administration and also the messaging between the processing units and memory and so on. So they have to be compatible. They have to be to take care of all of that stuff. Okay, is that clear so far, guys?
Yes, yes.
Yes.
Okay. This one distributed and this one is hybrid distributed shared memory. Last slide before the parallel programming. Okay, let us see here the largest and fastest computers in the world today employ both shared and distributed memory architectures. Actually, this hybrid system involves all of the shared and the distributed. So if let's say, for example, let us take the example of cluster. So if let's say this is a cluster, so maybe inside this PC here, we have a shared system, a shared architecture, shared memory architecture here and here. And all of them are linked through a very fast network. So this system will become hybrid, right? Or maybe inside the same machine, for example, one processor is quad core with a shared memory. So that quad core processor has 4 CPUs inside, and this this processor actually is one of, for example, 8 in the machine, or maybe 16. So for example, if the machine has 8 processors, and every processor is a quad core, for example, or octa core or whatever, and that quad core or octa core uses a shared memory, then all of them are connected together through the motherboard bus and everything. So this will become like a hybrid distributed shared memory, because now the processing units could be a component inside the server, and could be a complete machine that's connected to the main system through a network. Both concepts can be available. Both of the concepts are available really in the market. So here, that's why the largest and fastest computers in the world today employ both shared and distributed memory architectures. The shared memory component is usually a cache coherent. Yeah, because this one shared inside here. Then processors on a given SMB can address that machine's memory as a global. Okay, so this processors could access the memory of other processors. Okay, the distributed memory component is the networking of multiple SMBs. So here, to make it distributed, we have to link them through a network. SMBs know only about their own memory here. So the CPUs or this SMB knows only about its own memory, not the memory on other SMBs. Therefore, network communication are required to move data from one SMB to another. So here we have to have something at the middle, which will be responsible to exchange the data among those memories. Then here we have current trends seem to indicate that this type of memory architecture will continue to prevail and increase at the high end of computing for the foreseeable future. So this architecture actually is going to continue for the foreseeable future. Advantages and disadvantages, whatever is common to both shared and distributed memory architecture. So here, if there's any disadvantage for this shared memory, could be inherited here. Is there any advantage for the distributed? Also, it could be inherited by this hybrid architecture, and also the advantages could be inherited. Okay, here we came to parallel programming models. Do you think, guys, it's enough for today? Guys?
Wow, what do you mean enough, doctor?
If you